Hey everyone, I hope you're having a good week. So this is the first recorded lecture that I'm going to do for the time that I'm away. And what I want to start doing here is start off where we ended last lecture. So we were talking about for expressions, and I just wanted to walk through those one more time in a little bit more detail, a little more slowly. Okay, I've actually updated the slides here a little bit so to match what I wanted to say. So as I said last class, set comprehensions have been around a while, and that they correspond, at first pass, you can just think of them as being something like the Java foreach statement. So here's a foreach in Java where we have, a array in this case. And what I'm going to do is go through each element of the array and sort of add the number in. So actually I meant to do the sum here, but I forgot to update it. So in any case, you can see what's happening. I'm going to write it out here correctly. So this is the syntax in SCALA for actually computing the sum of the elements of the list. So just take this expression and substitute it over here, and you'd have the right thing in Java. Okay, and of course the distinctions here in the syntax, you can see in the for loop syntax, aren't too dramatic. They both have a for, they both have round brackets, they both have a statement afterwards. Actually in Java I'm required to have a semicolon here, which I left off. But the more substantive, syntactic difference is the type. So in Java we're required to put a type on this iteration variable, whereas in SCALA you're not required. In fact, I don't even know how to put one here. So it's always going to be inferred. So the way it happens is whatever the list that we're going through is typed at, so it'll be a list of something, so a list of t in this case, then if we know that xs is a list of t, then of course x must be a t, right? So that's what happens. And it'll go through and compute that sum. All right? So the way that SCALA actually implements this is using the foreach function that we talked about last class. So for this for statement is actually implemented directly as a call to foreach. And as I mentioned last class, really the reason for the existence of this for statement is in order to improve sort of readability of code. And as I also said, the for loop in SCALA is more general than the for loop that you have in Java. And so you can see that here. This is another example of the use of the for loop. And here I'm using the keyword yield. And what yield is going to do is turn this into a map. So when this is implemented, the for loop with a yield in it becomes exactly a map expression. And just to contrast that with the for each loop, you can see with for each, right, I'm not actually building a new list as the result. So if you actually just execute this thing, then you get, there we go, that's a SCALA fired up here. Here we go. So if we execute this thing, oh, I left out a colon. Sorry, I'm botching up my syntax. So that's what I get for typing things in without running them. There we go. All right, so there's the list 1, 2, 3, and now I can of course do sum over that list. And note that the return value here is nothing. I get nothing back. Whereas if I were to put a yield in here, it's now going to construct a new list for me. Of course, the list here is just unit, 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 because the return type or the value of a assignment expression in SCALA is unit. So I've got 3 units here. So note that the size is just like you would expect with map. The size of the result list is exactly the size of the argument list that we're going through. So that's how that works. And SCALA infers the types, as I said here, to figure out the type there. And for a map, it also infers the type inside of a map. There's one extra bit with a map, which is that Scala has to figure out not only the parameter x, or the iteration variable x type, but it also has to figure out the result type. And the way that's done is by looking at the expression e. We're just going to assume that x has type t, and then look at e and figure out what its type is. So you'll get the result type here. So we can also have conditions, as I mentioned, and these correspond to filters. So we can filter through. And we can, in addition, inside of a for loop or an iterator in Scala, we can flatten things and do stuff like that. So this is something I didn't talk about really in much detail last week, and I just wanted to walk through it. So how does flatten work? You'll see here what flatten is doing is taking a list. It's kind of like the identity function. If you remember the identity function, what does the identity function do? It goes on each element of the list, and it either returns nil, or it simply prepends the existing element onto a copy of the new list. Right? Flatten's doing a very similar thing, except instead of prepending, so note that it's a double colon over here on the left, and a triple colon on the right. So it's instead of prepending y to the front of the result, it is concatenating the things together. And so you can see that here on a example. So here I have a list of lists. So here's a list of lists, and on each element of this, when I flatten this thing out, what's going to happen? Well, we're going to take the function here and sort of execute it. Yeah. So we'll go down until we get down to nil. We'll return nil. We'll then take nil and prepend 10 in front of that. Concatenate it rather. So that we concatenate, we'll end up with the list 10. Then we concatenate 8, 9 in front of that. We concatenate 4, 5, 6 in front of that. And we just end up getting a longer and longer list. So the resulting list is eventually 110 nil. Let me actually just run this inside of Scala so you can sort of see what I'm talking about. Let's define that function. So there's the flatten function. And actually I can do this. Let's do this over in a file real quick. Yeah, so if you'll let me indulge me for a second. Here's a flatten function. And what I'm going to do is, we can actually relate that to the identity function. So here is the, let's just make this, there we go. So let's write out the identity function, if you remember that from last class. So the identity function looks like this. So the identity function, of course, is just going to go through a list and construct a new list that's exactly the same. So you can imagine running the identity function on a list of lists. Let's do the list, say 1, 2, with the list 3, 4, 5. All right. So if we think about how this computes, what's it going to do? Well, we're going to start with the identity there, and we're going to, of course, apply this function. And what that's going to mean is we're going to go here and choose this branch of the condition. So y will be equal to the first element of the list. So the first element of the list is, of course, this sublist 1, 2. And then the remainder is there. So that's the list 1, 2. And so what we end up with is taking out the first element and continuing recursively. Okay, so that's the first application. Then we're going to keep going. So we take the second element out, and that's now going to be the next element that we're going to prepend in front of our list. And finally, now you can see we hit the nil character, and of course when we hit the nil character is just going to return nil itself. So we end up with that. And now we've got our answer. So there's our list. It is the list 1, 2, 3, 4, 5, and that's the list. So it's actually the same list we started out with. If you look at the same sort of execution but for flatten, you can see it's going to follow much the same structure, except instead of identity, of course, we're calling flatten. So we'll replace all those through here. And actually, instead of doing double colon, it does triple colon. So I can just do a copy and replace throughout this entire section. And that's actually the result of doing flatten. So if you look at the final list, what is it? It's 1, 2, 3 concatenated with 3, 4, 5 concatenated with the empty list. And in this case, of course, what we're getting here is something, we can now simplify this expression. So we get the list 1, 2, well, actually, we can do it in the order, right? So it's the list 1, 2 concatenated with the result of doing this. So this is just, of course, the list. When we concatenate nil at the end, we just end up with that. So we can solve that. And now we can further solve this concatenation, and what it's going to do is just paste these two guys together. All right, so that's the result of a flatten. Everybody good? Yay. All right, so that's the identity function and flatten. I'll go ahead and put this in the slides so you can see it. Let's create a little note thing here, and I'll add these comments into the slides. Okay, so that's what I wanted to say there. Any questions about flatten? You can't ask me any questions. Isn't that great? Anyway, so I'm so used to asking if you have questions. But if you have questions about flatten, you should send me email, okay? So I'm very happy to chat with you guys via email. And please, pay attention to the Google groups while I'm gone. Maybe there'll be some back and forth there. Okay? So in any case, that's what flatten does. And it turns out that this flattening function is something that's also built into iterators in Scala. So if I have a nested iteration, so that's where I have one iterator drawing from a list, and then a second iterator which draws from the first iterator. In that case, what it's going to do is actually exactly what we've written. This is actually going to flatten out what's the result of the list. In this case, I'm actually just yielding the thing that I've seen. In general, I'm going to have a more complicated expression here. And what Scala is doing is something called a FLATMAP in this case. So I'd just like to walk through these very quickly. This is the map function, which hopefully you're all in love with now. So the map function, of course, takes a list argument and a function, and it applies the function to each element of the list. So starting one at a time, right? So we start at the first element, then the second, blah, blah, blah. Apply the function over and over. And not only that, we construct a new list with the results. So the size of the resulting list will be exactly identical to the size of the argument that we were giving to map. Okay? So let's look at FLATMAP then. So FLATMAP is, it looks very, very similar. What's happened in FLATMAP, instead of doing double colon, we're doing a triple colon. So this is concatenating everything together. Right? So this is going to apply and sort of flatten. And note that the types have to change. Because I am applying concatenation here, it's not true that the thing over here can be just any old thing. It actually must be a list. So if you look at the type of map, it takes the transformer x to y and produced a list of y's. So the results here are sort of accumulated together one after another into a list. Look at FLATMAP. Instead, we have a list of y's. So it's absolutely imperative that this function creates a list for us. And in fact, the result of the flat map is exactly the same kind of list. So whatever type of list f gives us, that's what we're going to give back to our user. So because instead of putting these things all together, prepending them into a list, we're concatenating all of the results into one big long list. All right, so you can see this happening here. Let's go ahead and type this stuff in. In fact, I'll do it in the monitor. So let's paste x.scala. I've got this stuff typed in. And what I've done is define this list x's, which is the list 0, 1, 2, 3, 4, 5. And I've typed in map and flat map. Okay? And you can see their types, right? So they're kind of similar, but they're not the same. Map will map to any y, whereas a flat map can only take a function which maps to a list. So what I'm going to do then is go ahead and map a function across. And the function I'm going to choose is a kind of funny function. So let's pick this function right here. This function is going to take its argument x and return a list. So I'm going to return the list of elements 1 up to whatever the parameter is. So now if I map that across my list 0 to 5, what I'm going to get? I'll get lots and lots of lists. So let's look and see what we get. First we get the empty list because that's 0. So 1 up to 0 is just 0. Then we get 1 to 1, then 1 to 2, 1 to 3, 1 to 4, and 1 to 5, okay, for the 6 different arguments that I provided. So that's what happens when we do a map. Look what happens when we do a flat map instead. Well, it's essentially what you can think is that it's doing the map and then flattening. So here, what we've got is the list. Note that the empty lists are just thrown out. We don't care about them because when you flatten, they go away. And we just have all of the interior content. So you can think of this as sort of taking a nested structure and reducing one level of nesting. So that's why it's called a flatten. This thing, a nested list, it looks kind of tree-like or something like that. You have a big thing with a lot of structure, and we're removing one level of structure here, which is sort of flattening things out. Okay, so that's the idea of a flat map. Here, just to emphasize, so we have, again, the list x's going from 0 to 5. And when I map that function across, what I'm going to get is this list of lists. When I call flat map, I get this flattened list, so just a single level list. Here's the same thing written out using the iterator syntax or the for syntax. Okay, so of course maps, we know, what do? We just instead of passing the function in here, we take that function out and sort of say, okay, well, x is being drawn from xs, that's here, and then we're going to yield whatever the result is of the function. So there it is, it goes there. Now with FLATMAP, it's actually a little bit trickier to sort of translate from this sort of what we need to do in the for loop to what FLATMAP actually does. Okay, so here's a flat map where I'm flat mapping that same function. So just taking a number and creating a list 1 up to that number. And this flat map, in order to do this, what we want to do is have 2 iterators. So the first iterator x drawn from the list we started with, and then that, what we're going to do is create another list from x. Then we need to draw out of that one. And in this case, we're just going to then yield the result. Okay, so for every x in the list, we create a new list, we draw y from that new list, and we yield y. Okay, so you can see here the length of the resulting list in this case is the sum of the lengths that result by applying this operation to every element of x is. So it's a little more complicated to understand exactly, what the length is going to be. With map, it's trivial, right? The length of the result is always the same as the length of the argument. With FLATMAP, you have to go in a little bit and to see what the result size is going to be. This is one use of the semicolon inside of the for expression. So this is where we have a for, where one of the iterators is actually mentions the iterator variable of the other. So the key thing here is that x is my iterator variable here, and it's being used to generate another iterator variable, and then I'm yielding. Okay, so this we call a nested iterator. Okay, and there's another use of this kind of semicolon, which is where we have independent iterators. So here I'm just going to give you a couple of lists. This has 7 elements. This has 11 elements. And what I'm going to do here is go through all of the elements of x's, then all of the elements of y's. And I'm just going to yield something stupid here. I'm just yielding unit. So you can ask, how many units do I get? So, and the way we can do that is just, I'm calling this prod for product. And in fact, the number of them, if you run this thing, is 77. So it is kind of amusing to see these stupid lists in SCALA. So let's go ahead and run that. And look, there's 77 units. Yay. It's kind of hard for us to see that, but it's straightforward when you call prod.length. You can see there's 77 of them. Yay. So it's just what you would expect. This is kind of like the Cartesian product. So this is going to run this expression for every possible pair of things drawn from x and then drawn from y. If you want to see the actual order that they're drawn in, it's easy to do that. So just yield something more interesting. In fact, we could just yield the pair x, y. Okay? And that'll sort of show you the order in which these are generated. So we get 1, 1, 1, 1, 1. So first, for each element of x, we go through all the elements of y. Then once we're done with that, then we go to the next element of x, go through all the elements of y, etc. All right. So that's the for syntax of SCALA. The book that you have, your textbook, has a really great bunch of discussion about this, and you can see in their chapter 23, For Expressions Revisited, they actually explain the entire implementation of these iterator expressions and how they're done under the hood. So it's an interesting discussion. The first discussion of for loops, actually don't, where is that? That's somewhere earlier in the book. Probably here. Yeah, for expressions, there we go. So in chapter 7, you can read about the basics of for expressions. So chapter 23 is a much more in-depth and sort of geeky explanation of how these work. So in particular, they talk about how to actually translate these things. So they use map, FLATMAP, and with filter. Okay. That is good. So that's all I need to say about for loops. So we'll go on then to talk about option types. Option types are not a hugely important topic, but they're interesting. And I think they're becoming interesting even more so in languages that aren't SCALA. So this is becoming something of I think, intense interest. So let's walk through it. So option types are like lists, but instead of having an arbitrary number of elements, they have only one or none. Okay, so I'll give you one thing, I'll give you nothing. Those are the only two options. With a list, of course, I can have an arbitrary number of things. So lists are properly more general than option types. So what good are these lists? Well, we can use them for all sorts of things, these little option types. In SCALA, the syntax for them is none. That's the empty option. and sum with an argument. So this is, there's something here, and it's 5. So this is a way of dealing with missing data that's safe. So you can think of none as sort of an alternative to null, and that's something I'll make more concrete before we end this topic. So here's an example of the use of an option type. So if you want to do integer division, it's important that we not divide by 0. So one way of doing division then is, instead of having our divide function return an integer, we can return an integer option. It says, well, if you want to divide it by n, well, maybe I'll give you something back. But if you give me a really crappy argument here, I can't actually do the division. So if n is 0, there's nothing I can do. I can't, there's no answer. So only if n is not 0, then I can return the answer, which is going to be the actual result of the integer division. This is kind of nice. It's you can think this is cool. It's like it's going to be safer. It does impose some stuff upon the programmer. We can do this in scheme, and when I did the scheme lecture, I showed you this scheme function. This is a safe divide. And in scheme, scheme is dynamically typed, so we could just simply return different things in the different cases. SCALA is not dynamically typed, so we have to have a type discipline here to explain the result, and option is the way we do that in sort of a typed language. Okay, so the thing that's imposed upon the programmer, though, is that we need to do something to handle the possible failure of the safe divide whenever you call it. Okay, so whoever wants to use the safe divide function, what they get back is not actually a number. They get maybe a number, and maybe a number is something that's not actually a number. And what this does is it forces you to handle this case that it's possible that there's nothing there. So in Scala, unfortunately, the syntax isn't really that nice for this. So what the standard thing to do is a match. So after we divide a by b, we then need to do a match, where if there's nothing, we have to do something for that case. And if there's something, well, then we have the result and we can actually do something with it. Okay, so that's actually how you need to use this kind of safe divide. As you can see, this is sort of imposing a burden on the programmer, in the sense that the programmer needs to always be aware that the bad thing could happen, and they always have to explicitly handle it. The sort of opposite design point is exceptions. So exceptions also exist in Java, and one thing we could do if there's a divide by 0 is to throw an exception. The difference here is that when we have a option type, the client programmer must handle that exceptional case. Whereas if we use Java exceptions, it's an option. The client programmer might handle the exception, or they might just let it fly. So there's also other things we could do, and sometimes we distinguish weird values of the possible type to indicate that something is missing or couldn't be done. So for example, in C, when you read a character, the characters are always going to be numbers between, if they're ASCII, 0 and 127. So, but the actual read character function in C returns a 32-bit integer. So actually, even if it's going to return Unicode characters, they'll always be positive numbers. They'll never be negative numbers. So the C get character function returns a negative number if the input has been closed, if there's no more data. The use of null in Java and similar languages, as well as the null pointer in C, this is also very standard sort of usage. So imagine you're looking up, a key in a hash table or something, and the key's missing. Well, one standard thing that hash tables do is they just return null for the result. So you're trying to look up in a dictionary, right? So a key value pair. If the key is missing in the dictionary, then instead of giving you back a value, what are they going to do? They could throw an exception, but usually they won't do that. Usually they'll return something like null. Okay. A standard example of this is indexing into a list. So, as you know, in Java, when you index into a list, if you go past the end of the list or before the beginning of the list, then you'll get an exception. An alternative would be to do it with option types. So this is a safe indexing operation where what we're going to do here is take a list of type X and some index into that list, and then we'll return the element if there is one there. If there's not one, we'll return nil. This is one way of doing this by counting down on in. So we start in at the initial value, and each time we recur here, we just subtract by 1 until we hit either the empty list, in which case we fell off the end of the list, or we actually hit the case where in is counted down to 0. So if we hit the end of the list first, well, we're screwed. But if we actually manage to get a element where in is 0, then we can just return that element as the result. Otherwise, we need to recur. So here we do the recursive case. So that's the safe way to index. And we can, of course, use that. This is actually not what happens in SCALA when SCALA does indexing. So SCALA uses the exception form, and it's really because the option type in SCALA, I think it's a little bit heavy. It's not a particularly nice design. It's not particularly pleasant to use, and therefore it actually isn't actually used that much. So in fact, people tend to do more just with exceptions. So here, for example, you take the numbers 10 through 19 as a list, and you try to get the 9th element, and here what we get is this. If I try to get beyond the 9th element, I get an exception. The apply, it's worth noting, is the method that is used to index into a list. And in fact, you can use the apply method without the explicit call to apply, simply by putting the argument in parentheses. So anytime you write this in Scala, any function application is actually translated to a call to the apply method for that object. We're going to talk a little bit more about that in the next lecture, so about the object-oriented parts of Scala and how it works. All right, so this is, not that great in Scala, I have to say. And in fact, it is really kind of heavy, the way Scala does all this, because in a sense, when you think about options, what is an option type? Well, it's a type that may have something or it may have nothing. So Scala has a real overabundance of ways to say that. So there's at least 3. So we have the empty list. Well, we may have a list that's not empty, but then we can have an empty list. We have the empty option type, where we may have some actual value there. And then we also have null. So null is a reference to nothing, where there might actually be a reference to something. And it's worth pointing out that unit is a different animal. Unit is not an option type. Unit always has nothing. So there is never any interesting thing about unit. And so unit is not in the same league here with these guys. So don't confuse that. These things are things that represent missing stuff where there could be something there. And there's a bunch of recent languages that have really simplified this a lot. And 2 of them really stand out. There's Swift and Kotlin. You can sort of click on these and look at these stuff. I'm just going to look briefly at Kotlin. Kotlin is a language really you can think of it as a SCALA minus minus. It's a simplified version of SCALA. And it has a couple of features that SCALA does not have. One of them is the one I'm about to show you. It's these nice option types. And this is also present with almost the same syntax in Swift. So the same design, more or less, in Swift. Okay, so what they talk about in Kotlin is the distinction between nullable and non-nullable types. So so we have nullable types and non-null types. And here's a nice example just to sort of demonstrate that. Here is a string type where I have the string ABC. In Kotlin, you cannot take this variable and then assign it to null. The compiler will complain because null is not a valid string. If you want to have a nullable string, you have to write the type as a nullable type, and the syntax for this in Kotlin is string query. This is nothing more than an option type. Okay, so it means maybe it's a string, maybe it's not. And what do they use to represent sum? Well, they just use the string. What do they use to represent nothing? They use null. Okay, so null is the representation of none and null in Kotlin. So it's nice that those two concepts sort of go away. And because non-nullity is encouraged in Kotlin programming, it turns out that people use these optional types now all over the place in Kotlin, as opposed to in Java or Scala, where they're in Scala where they're really quite rare. So one thing you can do is you can do a safe call. So this is the query dot operator. So query dot returns null if B is null. Otherwise, it actually invokes the method or accesses the field, whatever gets at that member, but only if B is not null. And you can chain these along. This is really quite nice. So if either Bob or Bob.department or Bob.department.head, if any of those is null, this expression will have value null. Otherwise, it'll actually give you the name. So that's quite pleasant. There's some further operators you find in these languages. There's the Elvis operator. The Elvis operator is, you can think of it's like, if the left-hand side is null, then give me the right-hand side. Otherwise, give me the value of the left-hand side. Okay, so it's called Elvis, I think, because it's supposed to look sideways, like it has big hair. I think this should be called the Trump operator now. It kind of has that like swooping hair if you look at it sideways. But anyway, this is named before our current president came into office, so it's the Elvis operator. So this expression then, what it's going to do, if B is null, of course the query dot operator will be null, and therefore the whole thing, this expression is null. So what the Elvis operator does for us, it's just a simple way of saying, if this left-hand side is null, then give me something else. So anyway, there's the sort of long form for that. Anyway, you can read about this. It's kind of interesting. And just to point out that option types are coming into the mainstream, and I think partially because of this kind of syntax support. So rather than having to write option int, you just write int question mark. And that's in Kotlin terminology, a nullable type. Okay, so that's all I have to say about option types. They do show up in Scala programming, so you'll see them, and it's important to be aware that they are there. I think I'm going to stop this lecture now, and I'll just produce another video. So rather than having one big long video, I'll break it up sort of into thematic parts. Okay, so I'm going to stop here and continue in a minute.